I'm going to go over some bonding notes and some naming notes, and we'll be starting specifically with ionic compounds. So first, let's talk about why do atoms or ions or elements bond with one another? So a chemical bond is simply an attraction between two atoms or two ions. And the reason that atoms or ions make bonds is that they want to become more stable. And again, to be more stable is to be more like a noble gas, so technically they're trying to get to that full valence shell. The results are that atoms are less reactive and more stable, and are technically at a lower energy level. And that's what their goal is. As a reminder, opposite charges repel. Just kidding. Opposite charges attract, where like charges repel. So remember, positives and negatives will attract one another, and charges like negatives and negatives will repel one another. So the type of bond that forms between two atoms or ions can often be explained by electronegativity, and we talked about that in our last unit. So electronegativity is the tendency of an atom's nucleus to attract the electrons, or the valence electrons, because those are often the ones that we're most concerned with, their own and any other atoms. So they're basically how attracted are we to the outermost electrons. And sometimes these are also bonding electrons, but we'll talk about that later. For right now, we're going to be concerned with the valence electrons. The trend of electronegativity is that it increases as we move from left to right, and it is also increasing as we move from bottom to top, so as we move up. So Flo over here is greedy, so she really likes her electrons. And Frank over here is Frank is fat, so that just means that he's really a big atom, which often means that he's not very attracted to the very outermost electrons. And so sometimes that's an easy way to remember that as we move toward flow, our electronegativity is increasing. All right. So there are three types of chemical bonds that we're going to be discussing, and we are going to be starting with ionic bonds. And we'll move into the other three on subsequent days this week. So ionic bonds are attraction between an anion. Oh, I should do cation first. So between a cation and an anion. And the only reason that I write cation first is because when we write the name or we write the formula, we'll also always write the cation first. And the cation is the positively charged ion, and the anion is the negatively charged ion. Your cation will also always be the metal, and your anion will be the non-metal. So this happens due to we'll do an cation losing an electron. That's how we become positively charged, to the anion, who then ends up gaining the electron, or electrons. It can be more than one. So here is an example of that happening. So sodium, remember, has one valence electron. And so it's going to want to get rid of that one valence electron. But really what's happening is that normally sodiums aren't alone in the world. And if they come near a chlorine atom has 1, 2, 3, 4, 5, 6, 7 electrons. So it wants an electron. Plus, chlorine actually has a high electronegativity. So what it actually is doing is that it's not only attracted to its own electrons, but it's so attracted to sodium's electron that it tears it off and pulls it over into its own shell. So now chlorine has gained an electron and become an anion, right? Because now it has an extra electron. And sodium now becomes a cation because it's lost that valence electron. And then the sodium and the chlorine become attracted to one another, and they stay near each other, and then they end up with an overall what we call neutral charge, a net neutral charge when they're near each other. And so when we write this, instead of writing this all out like this, we just write NaCl. But really what's happening is we have a positively charged sodium attracted to a negatively charged chlorine until they've basically canceled each other out, and then that is our ionic compound. So typically our metals have low electronegativity, meaning that they're not as attracted to their outermost electrons, and nonmetals tend to have a very high electronegativity, so they tend to be really attracted to outermost electrons, even other people's outermost electrons, so much so that they can steal an electron off. So sodium, if you look at the table above, has electronegativity of about 0.9, no units here. Chlorine has an electronegativity of about 3.0, so chlorine has a much higher electronegativity. When we see a difference that is this great, this will often result in an ionic bond. The result of an ionic bond is the formation of an ionic compound. Some examples are NaCl, magnesium chloride would not be another one. I don't know, potassium fluoride. I'm just making stuff up now. But basically it has to be a metal attached to a nonmetal. So those are ionic compounds. Now what we're going to do is we're going to learn how to name some of our ionic compounds. And we're going to start with type 1. Now, type 1 ionic compounds are single charged metals. That means that metals that can only come in one potential charge. And so type 1 metals include family 1. So hydrogen is technically not a metal, but lithium down are all metals. Hydrogen actually forms a 1+ ion as well. It's just not a metal. So lithium down are all 1+ charges, beryllium down 2+ charge, and then aluminum down is 3+. So remember, boron is also not a metal, so it's not going to count as a type 1 metal since it's not a metal. You will also have to remember zinc. Zinc is a 2+, and silver is a 1+. So a nice easy trick to remember this is aluminum is 3, so it goes 3, 2, 1. So these are all of the metals that you have to know or have their charges memorized. So family 1 is 1+, family 2 is 2+, aluminum down is 3+, zinc is 2+, and silver is just 1+. So here are our rules for naming an ionic type 1 compound. Now remember, it's got to be a metal bonded to a nonmetal. So a cation bonded to an anion. And we will always write the cation first. So here are the rules from going from formula to name. The first thing you're going to do is write the name of the first element. It should always be the cation. Then you're going to write the name of the second element using the suffix "ide." The anion will always be written second. You don't use any prefixes or Roman numerals. You just use the name of the first element. Second element ends in "ide." So here's our first example. We have Mg, that is magnesium. We have Cl, that's chlorine, but we take the second name and we use the suffix "ide." So I'm going to take off the chlorine part. So I'm going to take off the INE, and I'm going to replace it with IDE. So it's going to become chloride. So then the name is magnesium chloride. So pretty easy. Now, your question is probably, hey, what about that too? Well, you don't need to worry about that in the name. But when we go from name to formula, you do have to figure out what all of the subscripts would be. So the overall goal is to form a neutral compound. So let's take magnesium chloride, for example, first. Magnesium, if you look at it on the periodic table, you should see that it is in family 2. So magnesium actually has a 2+ charge. And chlorine, if you look at it, actually has a 1- charge. So if you have 1 magnesium and 1 chlorine, you end up with a +1 charge. So this whole thing is still attracting stuff. So what's going to happen is it's actually going to attract a second chlorine. And once you attract a second chlorine, then this charge and these charges cancel out, and you get a net charge of nothing. Once you have a net charge of 0, then it's not going to attract any more ions. So MgCl2 is then the ionic compound, and it won't attract any other ions to it because it's at a net neutral charge. So keeping that in mind for our next part, we're going to go from name to formula. And so again, the goal here is to form a neutral compound. So the first thing you're going to do is you're going to write the symbol for the cation, and then write the symbol for the anion, and then based on their charges, determine how many of each you must need to create a neutral compound. So we'll do CaCl2, so calcium chloride. So calcium has a 2+ charge because it is in family 2, and again, chlorine has a 1- charge. So if I have just 1 calcium and just 1 chlorine, well then what ends up happening is this still has a 1+ charge. So again, it's going to attract another chlorine. So when it attracts another chlorine, we'll say 1 more, now it has a net neutral charge. So we would write this as 1 calcium and 2 chlorides. You don't have to write the 1 because it's assumed. And you just leave the 2 so everybody knows that the calcium attracted 2 chloride ions. Now there is a trick that people do use for this, and they call it the swap trick, or I call it the swap trick at least. And so if I know that calcium has a 2+ charge and chlorine or chloride has a 1- charge, what I can do is I can take just the number portion and swap it into the subscript. And that will tell me how many of each I would need. Now, if you do the swap trick, you will have to reduce to the lowest common whole number ratio. So I'm going to give Ca2O2 as the example. So that's calcium oxide. So calcium has a 2+ charge and oxygen has a 2- charge. So with 1 calcium and 1 oxygen, you end up with a net neutral compound. Well, 1 calcium and 1 oxide look like this. Again, you don't have to write the 1s because they're assumed. Now, if you use the swap trick, what ends up happening is that you'll see that calcium has a 2+ charge and oxide has a 2- charge. If you take those numbers and you swap, you would end up with Ca2O2. So you would need to reduce that to Ca1O1. And again, you don't have to write the 1s, they're assumed. So anytime you're going to use that swapping trick, you have to make sure you reduce to your lowest whole number ratio. Again, I'll give you another example. If somehow you end up with, well, I guess you can only do 2. Well, I'll give you more examples when we get to ionic type 2 metals because we'll have more different ratios when we get there. So this is how you name type 1 ionic compounds. What you guys are going to do next is you are going to practice going from formula to name and then name to formula.